All right, the next operation we're going to take a look at is the Bitwise-AND. Now, we talked about the bitwise inverse in the last lesson. These lessons, these next 3 lessons, we're going to be talking about the bitwise AND, the bitwise OR, and the bitwise exclusive OR. The bitwise inverse had only a single element to it. In other words, you had an integer, a, and you wanted to take the bitwise inverse of it. All you had to do was just simply put the tilde in front of it. For the bitwise AND, the bitwise exclusive OR, and the bitwise OR, all 3 of those are going to require a second component. That second component is called a mask. Now, when we talk about a mask, we're not talking about some sort of like a mask on your face or anything. This is more like a silkscreen mask. A silkscreen mask allows, whenever you're silkscreening something, there's portions of the mask that keep paint from coming through to whatever you're trying to silkscreen, and then there's portions of the mask that are opened up so that the paint can flow through. This mask is a lot like that. There are going to be 1s and 0s. It's going to be a pattern of 1s and 0s that's exactly the same size as the value we're trying to manipulate. There are 1s and 0s in appropriate spots of the mask to keep an operation from happening to some bits, but allowing it to happen in other bits. Now, we're going to start out with the bitwise AND. Before we get started, though, let's do a quick refresher of what the AND operation looks like. Remember, the AND operation says I'm going to output a 1 only if all of my inputs are a 1, right? Now, in a bitwise operation, we're going to do the same thing, except we're going to do multiple AND operations at the same time. One AND operation across each column or each power of 2 bit for our number. So let's start out with an example. I'll have a value, and I'm just going to come up with a value. I don't know, how about 10101010? All right. And then I'm going to have a mask. And my mask is going to be 11110000. All right. Now, I am going to perform a bitwise AND between the value, and the mask. And what you're looking at is a bitwise operation is going to happen on each one of the columns. It's kind of like addition, except there's not going to be any carry. All right? So, what I've got is the 2 to the 0 column. There's a 0 ANDed with a 0. 0 and 0. 0 and 0 is just 0, right? Now, I've got the next column. 1 and 0 is, well, 1 and 0 is 0. Then 0 and 0 is 0. 1 and 0 is 0. All right? Now we move on to the portion of the mask where there are 1s. 0 and 1, well, 0 and 1 is 0. All right? 1 and 1 is 1. 0 and 0 and 1 is 0. 1 and 1 is 1. All right? Now I want you to take a look at what has happened in this operation up here. In the portion of the mask where there were 1s, the bits of the value were left alone. All right, it's kind of like the mask. It's the mask for a silkscreen mask. It was keeping the paint from coming through. It was making it so that the original value was left unchanged. In the portion of the mask where the bits were 0, it cleared the bits. All right? So what we can do is we can come up with a pattern of 1s and 0s for a mask that allows us to just clear, and the AND operation is only used for clearing. We can have a pattern of 1s and 0s in our mask, which sets up exactly which bits we want to clear and exactly which bits we want to set. All right? So, the bitwise AND. It clears bits where the mask is 0 and leaves bits alone where the mask is 1. All right. Now, let's do a real quick example here. And by the way, in code, some of you may have been frustrated by the fact that in a lot of our programming languages like Java and JavaScript and C and C++ and any other PHP, all those languages, that for some reason we use 2 ampersands for a logical if this is true and this is true. Why do we use 2 ampersands? The reason is because the single ampersand was already taken. It was used by Bitwise-AND. And so the Bitwise-AND, this guy right here, that is what identifies in our code the operation of a Bitwise-AND. So let's talk about something real quick. What if I have generated a random number and I want to make sure that that random number is even? My goal is to generate a random even number. Now, it could be done really easily with a bit shift. Okay, and it turns out, we'll talk about this in a little while, it turns out there is also a logical operation, or a syntax in your code to allow us to shift bits left and right. But let's generate a random number. How do we force it to be even? Yes, you could multiply by 2, but there's a way to do it with the bitwise operation. And the way is that we could clear the least significant bit. So let's say that we have a random number that's been generated, just called A. If I AND it with -2. -2. What is -2? Well, if you remember from your 2's complement, -2 is a bunch of 1s and then a 1, 0. All right? And so this mask right here is going to give us, it's going to clear the least significant bit of this by performing the bitwise AND. The only bit that's going to get cleared is that least significant bit. It'll clear the least significant bit, give us a random even number. I did say that this stuff was important, right? So, as a justification, so to speak, of what we're going to be talking about with these bitwise operations, let's go ahead and do it in some code. I have just a terminal window here opened up to my Raspberry Pi. Raspberry Pi, if you're not familiar with it, is a small board, a small single board computer that is based on the ARM processor that typically runs Unix or Linux, a version of Linux called Raspberry Pi OS. It's based on a Debian operating system. All of this stuff may be over your head, doesn't matter. It's a great little tool for learning how to program, to learn how to control things, to really be able to dig down deep into a processor. Now, what I'm going to be using it for here is really not anything special. I'm just going to be using it as a quick text demonstration of some execution of some code in C. Now, C is a rather old language, but it's still a very popular language. And I've got a compiler here. If you don't understand any of the syntax that I'm using, hopefully I will be able to describe it to you as we go along. So what I'm going to do first is I'm going to use a very simple text editor to open this file called bitwise.c that I have created, and these includes are just going to give us access to some functionalities, some libraries that will allow us to do some general I/O to the terminal and be able to show you exactly what the result of our operations are. And if you're not familiar with a programming language like Java or something that requires a main, basically whenever the code starts executing, after everything's been set up, we jump into our code at this position called main. And so here's where our code is going to start. So what I'm going to do first is I'm going to declare, and you probably, if you're familiar with Java, you're familiar with this idea of declaring a variable type. I'm going to declare a variable called color. And I'm going to set it equal to, let's see, the hexadecimal value 1, 2, 3, 4, 5, 6, and then semicolon. Now, the reason why I'm using the 0x is because we're going to be doing all of our representation here in hexadecimal. By doing this in hexadecimal, then you can be able to see where the nibbles start and the nibbles end. And the reason is because this color here, I'm basically going to be using 24-bit. So we're going to be looking at this as a 24-bit RGB representation of color. And by the way, the 2 slashes mean that everything after this point is going to be just a comment until we go to the next line. All right, so the other thing that I'm going to be using that may not be familiar is this idea of a printf statement. Now, a formatted print statement allows you to insert these little placeholders inside of a string to show where different values are going to be inserted. For example, I am going to put, how about hello, comma, and then I'm going to put %s, and then a period, or maybe an exclamation point, because we're really excited here, and then a \n. And what this string is saying is that I'm going to output this string. The %s is one of my placeholders. The \n means insert a carriage return. Now, for every placeholder that I put inside of my string, I need to put a value that's going to be inserted there. So I've put one placeholder there, and the %s means I need a string there. So I'm going to put, how about world? All right. And then when this string prints out, what it's going to do is print out hello, comma, and replace the %s with the value that first value that I've put in the comma after the comma here. So let's go ahead and save this. And then we're going to compile it. C is a compiled language, so you need to compile it first. And the compiler we're going to use is called GCC. And we need to tell it what we're going to be compiling. We're going to be compiling Bitwise-C. And then we need to give it the name. I'm going to use this -O switch in order to tell it the name of the file that I wish to compile it to. In other words, the output file. I'm just going to call this Bitwise. It's going to run, no errors, thankfully. And now to execute Bitwise, what I'm going to do is put a / to say that I want to execute out of the current folder that I'm in, and then Bitwise. And hit enter, and there's my hello world. It works just fine by inserting that world where that placeholder was. Well, what we're going to be doing is we're going to be doing a formatted string where I'm going to say something like, our color is, and then I'm going to put a %, let's see, how about a %lowercase x? And what a %lowercase x is going to do is that's a placeholder that says I am going to put whatever value is here, I'm going to put it in hexadecimal. So now if I put the variable, let's get of this quotation world unquote, and I'm going to put color here. Now I'm going to have, and in fact we probably don't need the exclamation point because we're not as excited about this, %x, now what's going to be substituted there is the hexadecimal value for color. Now it's not going to put the 0x in front of it, but you'll see that those values are going to be put there. And we're going to add one more thing here, and it's going to be a format, and it forces us to make sure that we don't delete any leading zeros, because remember, we're outputting a 24-bit color here, and it'd be nice to see all 6 digits of this hexadecimal value. So we're going to make sure that it outputs leading zeros by putting a 0 in front, right after the %sign, and then a 6 to say we want to make sure that 6 digits are output here. So we're going to save this, exit, we're going to compile it, run it, and there, our color is 1, 2, 3, 4, 5, 6. All right, now, this whole discussion is actually meant to talk about, well, bitwise operations. And the first bitwise operation is the Bitwise-AND. So let's take a look at the Bitwise-AND. If I wanted to, for example, just output the amount of blue, let's try doing this. So we'll do printf, the amount of blue in our color is. And I'm going to put the %0xx and then the \n. Now, what am I going to put here? Well, remember that color has all 3 colors in it, but blue is only the least significant 8 bits. So we're going to use a Bitwise-AND in order to clear out the other bits so that we can see what the amount of blue is. And in fact, since blue is only going to be 2 nibbles wide, we're only going to output 2 digits there. So we're going to do, the value we're going to pass is going to be color, all right, ampersand, and a hexadecimal FF. And this is going to give us the amount of blue. It's going to strip everything else off and output the amount of blue. Let's see what it looks like. All right, and the amount of blue, you see that that single ampersand cleared out the 1, 2, 3, 4, it cleared those bits to 0 and only left us with the 56. All right. In fact, let's make things a little bit more interesting. How about instead of including that in our print statement, we'll actually create some variables here. I'm going to create a couple more integers, int red, how about red spelt correctly, green, and blue. All right, I'm not going to initialize them just yet. I'll initialize them here. And what I'm going to do is I'm going to say red is equal to color ampersand 0x. Now red is the most significant 8 bits, so it's going to be FF0000. And those are going to clear out the green and the blue. And then what I want to do is I want to have green equal to color ampersand 0x FF00, because green is those middle two nibbles, right? And then blue, that's equal to color ampersand 0x FF. And so now what I can do is simply output blue here. But let's go ahead and output the red and the green too. How about printf the amount of red in our color is, and then we'll do %. Now, since it's a full one, well, let's just go ahead and do output 0 to x slash n, quote, comma, red, and we'll do the same thing for green. The amount of green in our color is, and we'll just go ahead and do %0 to, we'll see what happens, right? We're going to come in here and edit this again, so we'll see how this changes. All right, save it, exit, 1, 2, 3, compile it, run it. All right, now, it did separate things out, right? It made the 1, 2, the amount of red, it cleared out the green and the blue. For green, it cleared out the red and the blue, and then for blue, it cleared out the red and the green. But the problem is that the 1, 2, and the 3, 4 are shifted. They're all the way up to their original position. We want to shift them down. In fact, what we want to do is take red and shift it down 16 positions so that it's at the least significant bit positions. And we take green and shift it down 8 positions so it's at the least significant bit position. So let's go ahead and change that here. There's another operator, and what we'll do is we'll take this and we'll put those parentheses around here to make sure that that operation, the bitwise operation, is done first. And then we're going to do a shift right 16-bit positions. What this is going to do is make sure that our 2 nibbles, the 8 bits of red, are shifted all the way to the least significant bit positions. We're going to do a similar thing for green, except we only need to move 8-bit positions. So we're going to save it, exit, compile it, run it, and now we can see that our red is 1, 2, our green is 3, 4, and our blue is 5, 6. So that makes sense, right? Well, that's great to be able to pick apart the red, the green, and the blue from an existing number, but what if we want to set or replace a green or blue with a new value? For example, let's say that we want to replace green. We want to up the amount of green and make it so that there's now, I don't know, a hexadecimal DC there. That would be a different value, right? So let's make it so that we can replace the amount of green. Well, the very first thing we need to do is clear the amount of green that's there. So what we're going to do is we're going to say color, and we're going to use the bitwise clear, the Bitwise-AND, to clear those bits. We're going to leave the red there. We're going to clear the amount of green, and we're going to leave the amount of blue there. And so what we'll get is, let's go ahead and just output, we'll do another printf. Our new color is %06x \n and quote, and now we're just going to put color. All right. Now this is our color after we have cleared out the amount of green. All right, and now there's our amount of green cleared out. Now, when we get to the OR, we'll show exactly how to set those bits back to whatever value, or set them to the new value that we wish to have.